This video is about functions, and more specifically finding domains of functions. And when we talk about domains, let's start by looking at a function that we should know. This is our parent quadratic. And domains basically mean the x values that work, that you can put into the function and that you'll get an output. And for a function like this, or for this particular function, everything works. Every real number from this x-axis will produce an output. So this little notation here means our domain would be all reals. Here's another function. It's a cubic, and again this function would work for any domain value that we wanted to put in here. So again, our domain would be all reals. The two cases that we're going to look at that could be producing restrictions for the domain are having variable expressions under even index radicals. We'll use square roots in this video, or variable expressions in a denominator. These are the 5 functions that we'll look at. Starting with this one, we have a function notation over here which implies that this side is a function. And remember that when we're talking about a square root as a function, we are talking about the principal roots. Later on, when we start using algebra to solve inequalities, when we take square roots of both sides, we will do a plus or minus. That's in the process of the algebra. But in function notation, this means principal roots only. One thing that can be confusing when we're finding restrictions is whether our work is giving us values that do work or whether we're getting values that don't work. In this case, we want to find out which values will work as the domain. So we're going to make an inequality, anything under this square root, x squared minus 10. We are going to set it greater than or equal to 0. Because in order to take a square root, we need to have some kind of positive number under here. Or 0 would work also, but we cannot have a negative. That would produce an imaginary. So let's go ahead and solve this. X squared greater than or equal to 10. And here's where, when we take the square root of both sides, we will get plus or minus. So if we wanted to make a number line, we would put our two solutions here, negative root 10 and positive root 10. And we can see that putting either one of those values into this function will give us 10 minus 10, which is 0, which does work. So these will be good values for the domain. These do work. X-intercepts that are at root 10 and negative root 10. The values in between do not produce any outputs, but all of the domain values to the right of root 10, or in the positive direction, and to the negative direction from negative root 10 will work. So our domain, I'm going to use interval notation, would be from negative infinity to negative root 10, including, and then a union including positive root 10 to positive infinity. So once again, the process here led us to values that do work in the function as domain values. In this function, we have a different situation. No square root, no radical of even index, but we do have a variable expression in the denominator. Now what we're going to do here is we're going to take this expression and set it equal to 0. So we're solving the denominator for zeros. But what the result will give us are values that do not work. So in this case, when we're finished here, we will have the restrictions of the domain. So let's solve it. X squared minus x minus 2 is equal to 0. This one factors. There is another video about using the discriminant to help you determine whether a quadratic is factorable, which you could check out. This one was pretty easy. But what do we get here? We get x is 2 or x is negative 1. So what we now have, if I were to graph this out, is here's my 0 point, here's 2, here's negative 1. This tells me that this value does not work in the domain because when I input into the function, I get a 0 denominator which is undefined. Same thing happens here. So what this implies is that everything else will work. All of these values, all of these values, and all of these values. Now usually these also indicate the location of asymptotes, vertical asymptotes in the graph. They could also give us holes in the graph. Either one of those is possible. And here is the graph. We can see that there are two vertical asymptotes. One is at x equals 2, the other is at x equals -1. All the other domain values produce outputs and will be defined in this function. Now with this function, we have both situations. We have a variable expression in the denominator, and for this case we want to find restrictions, values that do not work as domain values. But at the same time, we have a square root with a variable expression under it. So we're also going to test using an inequality for values that do work. So first test is to find a restriction, and if x is 7, we end up with a 0 denominator. Now at the same time, I want to set this greater than or equal to 0 because it's also the expression under a square root, and I get x is greater than or equal to 7, but we just showed over here that x cannot equal 7, so I have to adjust this. Whoops. To x is greater than 7. And this ends up being the domain. So if I were going to sketch the graph of this domain, here's 0 and over here is 7, I would have an open point because it cannot equal 7, but all of the values to this side of 7 will be valid as domain values in this function. And here's the graph of the function. This graph right here continues upward infinitely, and we end up having a vertical asymptote at x equals 7. And you can see that the graph continues on indefinitely as we approach infinity. So our domain for this problem would be not including 7 to positive infinity. This is another example of a function with a square root, and the reason for looking at this is to compare with this. Let's look at the graph that we had for this problem again, where our domain values. So let's see what we get for this domain and then compare this graph. Let's set this expression greater than or equal to 0. We get x is less than or equal to plus or minus 3. Finding these solutions that will make this equal to 0, either -3 or 3 put in for x will give us a 0, and that does work for this function. My advice is to test 0. And what happens when we put 0 in for x? We get 9 minus 0, which does work. So these, and here's the graph of our function. From -3 to positive 3, and all the values in between, do produce defined outputs. So in this problem, our domain is from -3 to 3 inclusive. Alright, our last problem. We have both cases again. I have a variable expression under a square root in the numerator. So for this situation, I will be testing to find values that do work as domain values. Now my denominator has a variable expression, so I will also be testing for restrictions. Now these expressions under square roots, we said greater than or equal to 0. These values have to be positive or 0 in order to have a defined output. So we get x squared is greater than or equal to 5, x is greater than or equal to plus or minus root 5. So from -√5 to positive root 5, these values do work. Domain values that will work. Well, let's test 0 in the numerator. 0 produces square root of a negative. Now let's find restrictions. Let's set our denominator equal to 0. This factors to x. And here's where some students get confused when they see x equals 1. They assume this is a domain value, but what these are, again, are restrictions. These are the values that give us a 0 denominator. So where is 1 on this graph? It's somewhere in between here. So this value we can disregard because it was eliminated from this work that we did with our square root expression. But positive 3 is over on this side of, oops, that's supposed to be square root. Sticker is over on this side of square root of 5. So we will have a vertical asymptote at x equals 3. So let's take a look at this graph. This is our location of negative root 5. This is our location of positive root 5. Right here at x equals 3 is our vertical asymptote. And we always want to go least to greatest when we're writing this interval notation. Is from negative infinity to negative root 5, inclusive, because we can use negative root 5, and then a union. We skip over all these values and we pick up at positive square root of 5 all the way to our asymptote, not including the asymptote, and then a union picking back up after 3 all the way to infinity. Alright, keep practicing your functions.